circle will contain infinitely many values, and those, or rather points, not just values, and those points are related to, or relate actually, the angle formed between the positive x-axis and whatever the ray is going from with respect to that positive axis. And well, and and like I mentioned before, there's infinitely many points on the circle that live on the circle and unit circle, and therefore we will have pretty much infinitely many angles defining those points. But we were under the impression that there were only 360 degrees. Those are not infinitely many. Well, recall that a degree can be further divided into minutes and seconds, which is what makes it infinitely many smaller values decimals, all right? In a similar way that we can have a meter, which is divided into decimeters and then centimeters, millimeters, and essentially infinitely many small quantities. So it's true, this idea is also true for the unit circle. Sometimes it's like a bit complicated about what a unit circle is and that notation, symbols here and there, but all we need to do about this is this, that in each point in the on those order pairs in the unit circle contain an x component and a y component like any other point. The x component, the sine function, will be defined by the x coordinate, oh hold on, by the y coordinate of the value, which in this case this is our y, and the cosine function associates the angle with the x component of that given order pair. That's all you need to keep in mind for now. So x's and y's order pairs. X is cosine, y is sine. Something you may have seen before, maybe. If not, well, it's good to review. Well, so that's essentially our first main result, that all points are of this form. When we relate angles to order pairs, that's the form of the order pairs, and not the reverse. If you reverse sine and cosine with x's and y, you will get something different, and that's something we may get to see at the end of the semester if we do parametric equations, if not until you get to the end of Calc 2 and pretty much the whole Calc 3 semester, but that's something else. So for now, it's important to have our x's to represent cosine function and the y components to represent the sine function. And well, so for now, well, so we're talking about angles and the like, all right, but you might recall from last time we defined angles to be represented with Greek letters. In particular, the Greek letter theta, that is the lowercase theta from the Greek alphabet, represents angles for the most part because, well, that symbol is established to represent angles that are in standard form. And again, angles in standard form come from the unit circle for which the center is located at the origin with respect to the positive x-axis. That's what we mean by standard position. All right. So here we're going to define some of the trigonometric functions. Well, there's actually 6 of them. And you may have learned these trigonometric functions from a different approach, that is using triangles, using the SOHCAHTOA, SOHCAHTOA, right? That's one way, but that's going to come later when we apply this to triangle problems in which, yes, indeed, sine is opposite over hypotenuse and all that, yes. In the meantime, we are going to relate these 2 points on the unit circle, which you'll see how this point on the unit circle really create that right triangle, in fact. Well, so we already defined sine and cosine, for which cosine t for now equals x and sine t equals to y. Those are the 2 freebies. So every time we're given an order pair, we are already given 2 trigonometric functions, sine and cosine. Well, we can find the tangent function by finding the ratio between y over x, which is sine over cosine, and well, that's a ratio, an identity that you may know already, But well, again, you may have learned it from the point of view of right triangles, which is in this case opposite over adjacent, and then cotangent, which is its reciprocal, and then cosecant, which is the reciprocal of the sine function, which is y, or 1 over y, or 1 over sine, that's simply reciprocal, and the secant function, which relates the reciprocal of cosine, that's 1 over cosine, that is 1 over the x component, which is how we relate, how everything will be obtained from that given order pair. And let's do one example to find the sixth trigonometric function. So we're given just any random point. That random point lives on the unit circle. It's actually, what quadrant is that? Negative and then positive. It's on the second quadrant. All right? So sine. That's a freebie already because sine, this is simply the y component of the point. That's 2 root of 6 over 5. And cosine, that's simply the x, cosine t. All right, that's something already. You know what? Let's do this as a y, just so we can see where are we getting this from. All right, so from the identity that we have at the top of the page, tangent happens to be the quotient between y and x, which is sine over a cosine. We know y is 2 root of 6 over 5 divided by negative 1 over 5. And well, what do we have? We have a division of a number of a fraction by another fraction. Dividing by a fraction is the same as multiplying by the reciprocal. And also, check this out. We have positive divided by negative. So that's 2 root of 6 over 5, comma, that, times 5 over 1. And well, where's that negative? Let me put it over here. And simply divide out all the common factors. So tangent of this point will be negative 2 root of 6. So that's the tangent value. For cotangent, which is right below, is the last on the exercise, but well, there's a couple of ways we can go about it. So number one, just find the reciprocal of this number or go with the definition. I'd rather go with the definition so you guys can see where is this coming from. So cotangent, which is the reciprocal of tangent. If tangent is y over x, then cotangent is x over y. In this case, negative 1/5 over 2 root of 6 over 5. Same story as before, dividing by a fraction, that's the same as multiplying by the reciprocal, which is what I'm going to do here. So that'll be negative 1/5 times 5 over 2 root of 6, and then we can divide out the 5s like this. And then from there, how about we are left with negative 1 over 2 root of 6, which is essentially our final answers. However, when it comes to getting into the unit circle, defining values of trigonometric functions that contain radicals, usually we don't like radicals in the denominator, especially the homework system. So if you put this in your final answer, it may not take it as right. So it may tell you something that, although your answer is correct, it's not in the right form or in the right, or simplified to lowest term. Well, in this case, we're not going to simplify anything really, but rather we will rationalize the denominator. So rationalizing a denominator means to get rid of the radicals in the denominator because, well, in some cases they don't look pretty, so to speak. So that's mainly why we do that. And all we do is multiply numerator and denominator by the radical that we have in the denominator, that is the square root of 6. And well, multiplying across numerator times numerator, that's going to be negative root of 6 divided by 2 times root of 6 times itself, that's simply 6. So, and that's how we get rid of the radical in the denominator. So why does that happen? I'll explain that in a second. So in the end, we're going to obtain negative root of 6 over 12. So now, to explain the rationalizing thing, so that's square root of 6 times itself, root of 6. So one way to go about this is 6 raised to the 1/2 times 6 to the 1/2. Same base, and well, just add the exponents, 6 to the 1/2 plus a half. That's 6 to the first power, which actually kills the radical symbol. All right. So that's how the rationalizing works. Okay. So let's do the cosecant function. So cosecant happens to be simply the reciprocal of the y value of the given point, the reciprocal that is 1 over 2 root of 6 over 5, which is simply 5 over 2 root of 6. And again, in this case, we will have to rationalize the denominator once again, because we don't want these radicals in the denominator. Root of 6, and this is 5 root of 6 over 2 times 6, which is 12 again. Okay. And secant, it's nothing other than, what was that for secant? That's 1 over x, the reciprocal of cosine, 1 over negative 1/5. But this one doesn't need any rationalizing. We don't have any radicals at all. Dividing by 1/5 is the same as multiplying by 5. Well, negative, because we have a negative number. And that's how we get the 6 trigonometric functions for a value that it's not on the unit circle, actually. Okay, I mean that it's on the unit circle, but it's not, well, we don't know about the angle yet. Never mind. Let me rephrase that. Okay, so trigonometric functions for angles. Well, so what we did in the previous page was more like a generalization of how we can see all these points on the unit circle as a real number. So notice we didn't use the Greek letter theta. We use instead the letter t just to represent any value, any real number. But now that we already have an idea of how this works, now that we know that these points represent our representation of an angle with respect to the positive x-axis, going all the way to that ray pointing to the end point on the circle, well, we are now ready to talk about angles, and angles as as numbers, So in this case, we're going to change the t's with thetas. And what else? And why is that cosine theta equals cosine t and the like function sine theta sine equals t? Because again, the t was used for real numbers, but still, I mean, angles are pure numbers too. They're also real numbers. They're not imaginary numbers or complex numbers at all. They're still imaginary numbers, but now we are going to incorporate this notation just to denote that these functions are really functions of angles, even though, yes, again, these angles, these numerical values that represent angles are real numbers, regardless of whether you represent these angles as radians or degrees or decimals, you name it. All right. Well, trigonometric functions of quadrantal angles. Well, what do we have here? We have that picture of a unit circle. So for this, 0 degrees, 0 radians. Notice I represented this in both radians and degrees. How do we know which one is which? Well, because there's no degree symbol. That has to be understood to be, a radian. And if we see the degree symbol, well, then those represent degrees. And 0 degrees, it's the same as 0 radians. So there's really nothing crazy about it. What matters though is that at 0 degrees, I mean that's being exactly at the positive x-axis, and since this is a unit circle, this has to be the point 1, 0. All right. So that's the explanation behind of why is this point 1, 0. So from here we will define the 6 trigonometric functions. So sine theta which is y, cosine theta, which is x. Well, whenever you're given an order pair that is represented on the unit circle, those first two functions, sine and cosine, are already freebies because they're given, you know. So the x value is cosine, which is a 1. The y value, which is sine, that's a 0. That's it. The tangent function, tangent theta, that's y over x. In this case, y, which is 0, over x, which is 1, that's equal to 0. Now that we have the tangent function, we may go ahead and define the reciprocal of tangent, which is cotangent. I'm going to put it below. Cotangent theta, that's x over y on the other hand, and that's in this case 1 over 0. It's the reciprocal. And what's 1 over 0? Undefined. Right, careful. That's undefined. Cosine, well, its reciprocal happens to be secant. The secant function, that's 1 over x, and in this case that's 1 over the quantity x, which is 1, that's simply 1. No problem with this one. And lastly, cosecant, which is the reciprocal of sine, which is 1 over y. That's the reciprocal of sine. That's in this case, we have special effects today. That's 1 over y, and that's what? 1 over 0, right? And what's that again? Undefined. All right. Let's do the same for the values of the trigonometric functions corresponding to 90 degrees. And again, and by the way, notice how we have this 90 degrees also represented in radians, and that is in terms of pi. Well, by the way, radians don't have to be always in terms of pi, because again, keep in mind that pi is an irrational number, and it's not always possible to get a number doing calculations and obtain exactly pi on the calculator. That'll be weird if we got something like that. But mostly, you will see this pi symbol for angles that are multiples of 90 degrees, multiples of 45 degrees, 30 and 60 degrees. All right. For other weird angles, well, we may still see. Never mind. We may still see other angles, pi over 8, pi over 16, pi over 12, but those are going to come later when we look at half angle, double angle, multiple angle formulas. Well, in the meantime, let's get our trig functions for 90 degrees. So that's a sine theta equals cosine theta equals, well, again, when we're given an order pair from the unit circle, that's the advantage. So again, that's the advantage of having our points on a circle, because that order pair already gives us two trigonometric functions. So that's a y, that's x, and well, the y value, that's 1. The x value, that's x. That's sine and cosine, respectively. Oh, hold on. That's 0. So from here, we may go ahead and write tangent. Tangent theta. Well, tangent is the quotient between y and x. And well, y over x, in this case, that's 1 over 0. Well, that's undefined. So that's an undefined value. We can divide by 0. What about the reciprocal of tangent, in this case, cotangent? That's x over y. In this case, well, that's simply 0 over x. Oh no, 0 over, what the hell am I thinking? It's 0 over 1. And that's simply 0. Let's keep going backwards. Okay, cosine, the reciprocal of cosine, what's that? Which one is it? Secant. Secant theta equals, well, the reciprocal, 1 over x, and that's 1 over 0, another undefined value. Right? And last but not least, there's only one more function missing, that is cosecant. And that happens to simply be the reciprocal of y. That's 1 over y, which is 1 over 1, and that's simply 1. All right? Of course, we can keep doing this for what's the next quadrantal angle, isn't it? 180 degrees, and then the next one have about 270 degrees. Well, if you want to, to do it on your leisure time, that's fine. Essentially do the same, just define the point for 180 degrees, that's negative 1 comma 0, and the point 0, negative 1. Those are the points for the corresponding quadrantal angles, all right? However, we don't have to do the whole thing. It's enough to look at these two and then simply see a pattern. And actually, if you want to do those at home, you will see those results. The 180 and the 270 degrees are going to give us this series of values in the same way that we got for 0 and 90 degrees. Let's compare. Okay, sine of 90 degrees. So 90 degrees is 1 for sine, 0 for cosine. In the same way, well, let me highlight them. So sine equals to 1. Cosine equals to 0. That matches here. Tangent is undefined. And what else? Cotangent is, cosecant is 1. Secant, it's not defined the same way. And finally, cotangent is 0, right? So we can verify that from the table. And of course, you don't have to memorize these tables. After a while, after we are working with this kind of functions in applications, or when we employ this with, manipulating, what's it called, the identities, equations, you guys, it will be for you guys second nature to just coming up with these values from the top of your head. You'll see. All right, so that's for quadrantal angles. And again, quadrantal angles are the angles that lie in between two quadrants. That is, or angles that lie on an axis themselves, like the positive y-axis, that's 90 degrees. The negative x-axis, that's 180 degrees. Negative y-axis, that's 270 degrees, and then positive x-axis, which could be either 0 degrees or 2 pi or 360 degrees. And again, rotations, multiple rotations, which, well, we're going to talk about the periodicity of this kind of functions. Well, I think we already did, never mind. But we're going to get into that later again. The exact values of the trigonometric functions for 45 degrees. You may know this already. When you want to find 45 degrees, that's root of 2 over 2, comma, come on, shit. That has to be something like this. Root of 2 over 2, root of 2 over 2. All right? So, well, and again, same approach. The y value is sine, the x value is cosine. All right? But where are these coming from anyway? So that's the fun part that I would like to go over to. So, well, how do we form a 45-degree angle? The 45-degree angle is actually the intersection of number 1, the unit circle, which is what we have as a basis here, and whatever forms a 45-degree angle. But what's that whatever thing that forms a 45-degree angle? It's actually this diagonal line, which is defined as y equals to x, right? That forms a 90-degree on both the positive x-axis and the positive y-axis. But of course, our focus is the positive x-axis. So, when we think of points of intersection between, yes, this is the circle right here, and the line, they're intersecting at that point. How do we get that point of intersection? Any ideas? What would you do if you were asked, find the point of intersection between the line and the circle? What would you do? Well, even a wrong answer, come on. even if it's wrong? No? Well, create a system of equations. Y equals to x, x squared plus y squared equals to 1. Create a system of equations, set the equations equal to one another somehow. Well, in this case, this happens to be a non-linear system of equations, all right? So what's that going to be? Well, so this one is really easy to do by substitution. Every time you have like a linear with quadratic, I think substitution is the best choice. In this case, well, what you want to do is, how about replace y equals to x and replace this with an x, knowing that y equals to x, and well, from here, so substitute, that's x squared plus x quantity squared equals to 1, that's x squared plus x squared equals to 1, 2x squared equals to 1. And if we keep solving this for x, that's going to be x squared equals to 1/2, and x equals to the square root, or rather plus minus 1 over root of 2. And well, that's the same as saying plus or minus root of 1, which is 1, over root of 2, and that's rationalizing x equals plus or minus root of 2 over 2. So that's one of the values, isn't it? Root of 2 over 2, but I'm getting two results because I'm using the quadratic, I'm solving a quadratic equation. Where is that negative going to go to? Well, you'll see. But well, we only have the x values, but we know that y equals to x, so y will be simply plus minus root of 2 over 2. Well, that means two order pairs, negative root of 2 over 2, comma, negative root of 2 over 2, and root of 2 over 2, root of 2 over 2. Sounds good? All right, so this is the positive root of 2 over 2, but again, keep in mind that this line, this diagonal line, also intersects that point, which happens to be negative and negative. That's this point. So, and well, so if you ever wonder where these values for the trigonometric functions for 45 degrees, well, that's where, right? From finding the intersection between the circle, the equation of the circle, and the equation of the line, all right? Now, they're asking us to find the exact values of the 6 trigonometric functions for pi over 4 or 45 degrees. Well, we're given the following already. We're given that unit circle, that order pair, root of 2 over 2, comma, root of 2 over 2. And well, that's 45 degrees. 45 degrees or pi over 4. So that's our given. We already got those values from, well, the derivation we just did. And again, whenever we are given an order pair, that means two freebies here, the sine function and the cosine function. So sine theta, which is, well, the y value, cosine theta, which is the x value. And well, in this case, it happens that both the x value and the y value, they are the same. So simply go about root of 2 over 2, root of 2 over 2. Now let's go with the tangent function. For the tangent function, tangent theta equals to the ratio of y over x. And well, that's actually simple. That's just root of 2 over 2 divided by itself. And a number divided by itself, it's simply going to give us 1. How about cotangent? Cotangent theta equals x over y. That's, well, same value. So let me do it again. Root of 2 over 2 divided by itself, root of 2 over 2. I know it's kind of silly to write down the whole thing again, but again, in this case, y and x happen to be the same value. So that's going to be, what's that? 1, and cosine, or cosine, which will give us the secant function, that's 1 over x, which is 1, careful with this one, root of 2 over 2. So again, dividing by a fraction, that's exactly the same as multiplying by the reciprocal. So that will be 2 over root of 2, and you might want to rationalize this denominator because again, the ALEKS system may not like radicals in denominator, so let's rationalize by multiplying by root of 2 and dividing by root of 2. So that's going to give us the following with 2 times root of 2, that's simply 2 root of 2, and root of 2 times itself, essentially the radical canceled, and we are left with the quantity inside of the radical, which is 2. Cancel these 2's, and this will be simply root of 2. All right. Last but not least, sine, which will give us its reciprocal as cosecant theta. That's 1 over y. And check how, again, this is going to be exactly the same value. 1 over root of 2 over 2. And, well, I don't want to repeat this whole process again. Well, do the reciprocal, rationalize, simplify, final answer. So that should give us root of 2. Simply root of 2. So those are the values of the 6 trigonometric functions for the 45-degree angle or pi over 4. Of course, we can do the same right here. Like, check this out. Like, we can have a 45-degree angle in the second quadrant, but that'll be for what? Is that 3 pi over 4? Which is 135 degrees. However, this point root of 2 over 2 will be reflected about the y-axis, changing the sign of the x point, of the x value, to negative root of 2 over 2, root of 2 over 2. And well, if you were asked to find the trigonometric functions for the 3 pi over 4 or 135, well, it's the same reference point, root of 2 over 2, however, changing the sign of the x component, because, well, that goes with the direction and the location where the point will be, negative in the x direction and still positive in the y direction. We can still do the same for, what's that, 5 pi over 4, or what's that, 180 plus 35, that's a 210 or 215, I believe. 215 degrees, and in this case, same reference point. However, notice how this is in the third quadrant, and therefore both values are negative. And the same the 6 trigonometrics work, the same 6 trigonometric work. They work the same, finding the same ratios. Sine is y, cosine is x, and the reciprocals and the ratio ones. If they work the same, what might change in the end, it's just the sign of the y, of the sign of whatever value, depending on the function. All right. Of course, we're going to look at a summary of all the multiples of 45 in the same way that we will eventually look at the summary for the values for 30, 60 degrees. Well, it's coming up next. And of course, yes, we will do the derivation for where are the values for the trigonometric functions for pi over 3 and pi over 6 come from. So let's see. Yes, well, in this case, we will have some combination of unit circle and what's that? A right triangle approach, and that's so we can find the values, the points. So this is the real trick here. The real trick here is to impose a Cartesian plane for this triangle. Okay? And essentially, we're going to have the following. There is a circle going on here. All right? So what we're looking is this coordinate right here, and I'm going to give you the result. That result is 1/2 comma root of 3 over 2. Okay, and that's a coordinate that you may be familiar with. You may have seen it before. But again, where is this coming from? So we're going to use a combination of geometry and some algebra to derive these two values. So well. So this is what we're going to do in this case. Notice, so our A in this case is 1/2 and our B is root of 3 over 2. So I'm giving you the results. We're going to obtain those results. All right. What's this? So this is a right triangle. The one right next to it's not a right triangle. In fact, it's an equilateral triangle here, this one. It's an angle, again, an equilateral triangle. It's a triangle that has the three sides the same length. And in fact, this particular triangle, it's called the unit triangle. And we call it the unit triangle because the lengths of the other side of its sides that equals to 1. All right? And we're going to use that principle here in order to obtain that half and that root of 3 over 2. Can we make this look like a half? Got it. Okay, so we're given a triangle that apparently looks like just randomly made. No, it's not really randomly made. Well, we have 60 degree, 30 degree. But we are bounding, so to speak, the triangle to have its hypotenuse to measure only one unit. And well, this one unit can be your favorite meter, centimeter, feet, whatever. It doesn't matter because we're not incorporating any physical context at all. It's more like a geometric context here. So duplicating this triangle creates again our equilateral triangle, which is 1, 1, 1. But hold on. This 1 right here is given in a special way. So from here, if this length from this vertex to that vertex equals to 1, that means that we can write an equation that says A plus A, which is how many A's? 2 A's. So from here, 2A equals to 1. All right? What's A then? Isn't that the 1/2 from the x component for the 60-degree angle? How do we get that? How do we get the B value? Well, how about we forget about the equilateral triangle and we go back to the right triangle because, well, what do we know? We already knew this one right here. That's one piece of information. We got now the second piece of information. How do we get that third piece of information? We have the length of the hypotenuse and the length of one of the sides. How do we get the other side? What was that again? I heard something here. Pythagorean theorem, that's correct. A squared plus B squared equals 1. We know A is 1/2 quantity squared plus B squared, which is what we want to know. And, oh, hold on, that's not 1. Let me call it C squared. Well, it will be 1 anyway, but I was making a silly mistake. That's 1 squared. So that's 1/4 plus B squared equals to 1. Let's subtract 1/4 from both sides. That's going to be B squared equals 1 minus 1/4. That's the same as saying B squared equals to, is that, what's that, 3/4? And take the square root on both sides. What's that going to give us? Plus minus root of 3 over 4. And in this case, that's a B equals to plus or minus. Well, in the numerator, root of 3, unfortunately, is going to be left as root of 3 because it's not an exact value. But good thing the denominator root of 4 equals to 2. And that's where are these values for sine and cosine for the 60-degree angle are coming from. Again, it was a basic geometry problem for which we had to write a baby equation here to get the a, to get the x component, and then just use our favorite Pythagorean theorem to find the missing side, because we already knew another side on top of that. All right? What's next? You know what?